Jai Hind. My name is Arun Kumar Maurya, Assistant Professor in the Department of Electrical and Electronics Engineering at AKGC Ghaziabad. In the continuation of my lecture series on the special topics of power system transition and distribution subject, the today topic is electric power cables. Actually, this topic is very important for the training and placement related drives and the competitive examinations as well. And most of the questions are asked in a multiple choice questions of various examinations, and simple we can say that in a interview questions. So by this reason, I have seen this topic is very much important and take it as my lecture. So if I talk about the contents, what are the highlights and what are the things which I would discuss with you all. So the first one is dielectric stress in a single core cable, and after that we will see the maximum and minimum values of potential gradient, and after that we will see the grading of cables, and other one is disadvantage of intersheet grading. So first one is dielectric stress in a single core cable. In this case, under operating conditions, the insulation of a single core cable is subjected to a electrostatic stress. This is electrostatic stress called the dielectric stress. So in 2 marks, the question may be asked, what do you mean by the dielectric loss for single core cable? So we will easily see that definition. The insulation of a single core cable is subjected to a electrostatic stress in the cable, that is called as the dielectric stress to the cable. If we talk about the formulation part and the designing part, we will see, since single core cable is a form of cylindrical condenser, therefore electric intensity at a distance x from the center O of the cable is given by the expression. We will see in the diagram. Single core cable is a form of cylindrical condenser, therefore the electric intensity at a distance x. So we will see it is that this is the center point O. From this is the center point O, the distance is taken to be x, and this is the distance x. Okay, and this is the cable, so this is point O. So we will see this is small, capital D, so this distance is d by 2, and this one is it is not a circular part, it is a cylindrical part. So the distance is d by 2, and this is also d by 2, that is to be d by 2 into 2, that is d. This, so this is d, and that distance is taken to be, this is d by 2. Okay, so the formula is taken to be x, Ex equal to P by 2 pi epsilon naught into epsilon r into x. X is basically at a distance from point O, equal to Q by 2 pi epsilon naught into epsilon r into 1 by x. Okay, so this is the electric potential E in terms of volt per meter. So we will see the per meter voltage, and we will have to calculate the dielectric stress for a single core cable at a distance of 5 meter, 6 meter, 3 meter, depending upon the application. So the formula is to be taken as Ex equal to Q by 2 pi epsilon naught into epsilon r into 1 by x volt per meter. Actually, the unit is so important. This is volt per meter. In the other side, G equal to Q by 2 pi epsilon naught into epsilon r into 1 by x. This is the another expression, and V here it's a V equal to 2 pi epsilon naught into epsilon r and logarithm, that is log d by d. What is capital D and what is the small d denotes? So the capital D is a, actually you can see that the distance or radius which we can see, this is d by 2, and the total distance you may see that d by 2, so this is D, capital D, and the small d denotes the circular part of inside a single core cable, that is to be small d by 2. So this is the total diameter, so d by 2 into 2, so d. This is inside and this is for outside. So this is formula, this is a formula which is taken to be reference for calculating the electric potential, that is Q by 2 pi epsilon naught into epsilon r logarithm base E capital D by D. After that, substituting the value Q from the above expression, so that is to be Z equal to 2 pi epsilon naught into epsilon r V by log D by D, okay, and multiplied by 1 upon 2 pi epsilon naught epsilon r into 1 by x, so the Z equal to V by x logarithm D by D volts per meter. So this is the concluded formula. Since potential gradient G, what is G is basically a electric potential gradient which is varies inversely as x. Obvious from the above expression, we may see the Z equal to V by x log Arun D by D. So G is directly proportional to V and G is indirectly proportional to x. What is x? X basically the distance from the center of the point, that is to the cable, that is O. So this is the distance of x. It is inversely proportional. So since the potential gradient G varies as x, obvious from the above expression, therefore potential gradient will be maximum when the x is minimum. So that is x equal to d by 2. The potential gradient will be minimum when x is maximum, that is x equal to capital D by 2. So we may easily conclude this thing. This question may be asked in a multiple choice question or a short questions in AKTU or other competitive examinations for the conventional paper. So this establishes the relationship between the potential gradient G and the distance, that is x, for a dielectric stress in a single core cable. This may be asked in an interview also. So this is the major point to see the inversely proportional between the G and x. So when we will see the maximum and minimum values of potential gradient, basically it is a electrical potential gradient, that is Z. So Z max, when will be the Z max? So Z max equal to, from the last slide we will see the gradient will be maximum when x is minimum, x equal to d by 2. That is minimum, and potential gradient will be minimum when x is maximum, that is d by 2. This is the term which you have to follow in this case. So G max equal to V into d by 2, that is to be x logarithm d by d. So this is G max equal to V, that is to be x, that is to be d by 2 into log d by d base e. So 2 comes to be upper side, so G max equal to 2V d logarithm d by d. So this is the case of G maximum. Okay, electric potential gradient would be maximum at this case. By this formula, the calculation to calculate the potential is very much easy, and this is taken for your simple questions just like that, to interview questions. What is the maximum value of electric potential when the d is 4 centimeter, 5, 6, 7, 8, etc. So the G max is to be calculated, and other side is G max equal to 2V d log e d by d volts per meter. Okay, hence the ratio between the maximum gradient and a minimum potential gradient, that is actually here it is, this is G minimum, the printing mistake is there. So the G max and G minimum, this is the ratio. So 2 V by D log d by d and 2 V by D log base e d by d. So this is to be taken as G E max divided by G minimum, that is comes out to be this is very important relationship of the G max and a G minimum, that is ratio to be calculated as capital D by small d. So we have to ensure in our mind what is capital D and what is small d. So once again I am telling you, the inside cable or a circular part, the radius is to be d by 2, and the outer side part, this is capital D by 2. So this is very important thing to consider and to kept in a mind for a reference purpose, to see the what is the G max and the G minimum ratio, that is to be capital D by small d. Capital D, which is outside of a cable, and this is inside. Okay. Another part is grading of cable. What is grading? So grading is defined as the process of equalizing the stress in a dielectric of the cable. So grading is that it is defined by the process of equalizing the stress in the dielectric of the cable. Generally, the electric stress is maximum at the surface of the conductor or innermost part of the conductor, while it is minimum at the outermost sheet of the conductor. This is very important. The stress, we may see, easily see, the stress is maximum at the surface of the conductor. This is surface of the conductor or the innermost part of the conductor, while it is minimum at the outermost sheet of the conductor. This is outermost sheet. So in the outermost side, as far as we move uh, from the inner part to the outer side, the electric stress would be decreasing. So the innermost part of the conductor and the surface of the conductor, it is high. Okay. If the stress is equal to all the dielectric of the conductor, then the thickness of the conductor is reduced. But if the stress is maximum at any of the dielectric, then it increases the thickness of the cable, due to which the cost of the cable also increases. These are the small points, but important points, important things to ask as a question, as a multiple choice question, or a multiple selective question, or a short questions, I believe. So this is very important. Other thing is that capacitance grading or a dielectric grading. In the very first slide, I have told the few things, few important parameters to see the electric power cables. So in this case, the capaciting grading or a dielectric grading is seen. So in this type of grading, the homogeneous dielectric is replaced by the layers of dielectric having of a different value of relative permittivity. I I will once again repeat this thing. In this type of grading, the homogeneous dielectric is replaced by the layers of dielectric having a different value of relative permittivity. For getting a uniform stress, an infinite number of dielectric will be required, because the number, that different type of number of values of relative permittivity is to be taken as a capacitance grading. For uniform stress, an infinite number of dielectrics will be required. The electric stress can be uniformly distributed by using or two or more dielectric having a suitable permittivity. So we may easily see in the capacitance grading or dielectric grading in this thing. This is the radius that is to be small r, and if we talk about the red part, so this is to be r2, and if we talk about the green part, that is to be green part, it is r1, and the outermost part that is to be shaded as black, that is to be r. So the dielectric stress can be uniformly distributed by using two or more dielectric having suitable permittivity. So if we see the capacitance grading, so Gx equal to Q, that is taken as charge 2 pi epsilon naught epsilon r into x. What is x? X is the distance from the point O, that is the center point, which is x. Let us consider a cable having three dielectric of relative permittivity, that is E1, epsilon 1, epsilon 2, epsilon 3, such that in a relationship epsilon 1 is less than epsilon 2, which is also epsilon 2 is less than by epsilon 3, that is epsilon 1, epsilon 2, epsilon 3. This is the relative permittivity relationship for a particular case. Let R1, R2, R3 and R be the outer radii of the dielectric, that is to be R, this is R2, this is R1, and this is to be R. So if we see the potential, that is to be V1 equal to Gx into dx. The radius to be taken as the lower limit is small r, that is to be taken as this part, this is small r, and the outer part is R1. So V1, the electric potential V1 equal to G of x dx, and the limit is from R to small r1. That is, what is dx? Dx equal to q by 2 pi epsilon naught into epsilon 1. Epsilon 1, what is it? This is epsilon 1, and this is 2, and this is 3. So q by 2 pi epsilon naught into epsilon 1 x into dx. So v1 equal to q by 2 pi epsilon naught into epsilon 1 ln small r1 divided by small r. That is to be taken as v1, and v1 is also to be seen that the q by 2 pi epsilon naught into epsilon r into r, the multiplication of a small r. So that is to be the g maximum for the one side. So g maximum into r ln r1 by r. We have easily seen the z maximum when the z is inversely proportional to the x. So just like that, v1, v2 is to be taken as z max to r1 ln r2 by r1, and g max and the v3 is to be taken as v3 equal to g max 3 r1 into ln capital R, that is to be r3. It is the outermost part, that is to be capital R by small r2. So the v1 is g max r into ln r1 by r. So this is g1 v1, and v2 is g max to r1 into ln r2 by r1. R2, this one here inside, and r1 is a here inside, and r2 is for that side, and the v3 equal to g max 3 into r1 ln capital R by small r2. So this is the pattern of 1, 2, 3, and correspondingly the relative permittivity is epsilon 1, epsilon 2, and epsilon 3. So the total potential difference between the core and the earth sheet is to be as V equal to V1 plus V2 plus V3. So the total V equal to G max of 1 into R into ln R by R1 by R plus G max 2 into R ln R2 by R1 plus G max 3 into R into ln R by R2. So the total capacitance of the cable is C equal to Q by V. What is Q? Q equal to CV, and I wish to calculate the total capacitance. So the C equal to Q by V. So C equal to Q by V, that is to be Q, and the V of it this side. So this is inversely side. So Q by 2 pi epsilon naught 1 upon epsilon 1 ln r1 by r plus 1 upon epsilon 2 ln r2 by r plus 1 upon epsilon 3 ln r by r2. So the C is calculated as 2 pi epsilon naught divided by 1 upon epsilon 1 ln r1 by r plus 1 upon epsilon 2 ln r2 by r plus 1 upon epsilon 3 ln r by r2. So the capacitance maximum stress is given by G max of 1 equal to Q by 2 pi epsilon naught into epsilon 1 r, and for G max 2 also and G max 3 also. So when the G max 1 equal to G max 2 into G max G max 3, which is equal to the G max, so epsilon 1 r, epsilon 2 r, and epsilon 3 r, which is to be equal. So the voltage applied across the cable is equal to G max taken to be as constant small r ln r1 by r plus r1 r2 by r1 plus r2 ln capital R by R2. So Gmax represent the peak value of the electrical stress, and all the voltages are represented in the peak values, not in RMS value. It's an important point. So when we see the intersheet grading, in this method of intersheet grading, a homogeneous dielectric is used. But it is divided into the various layers of metallic intersheets between the core and the load sheet. This is the load sheet, and this is the core part. So the different calculated parameters. So if we talk about this is dy by 2, and if we talk about this is d1 by 2, and this is d2 by 2, and this is total d by 2, and Gmax is the gradient, and this is the intersheet of 1, and this is the intersheet of 2, and other part is the lead sheet. So the intersheet are held at a suitable potential which are in between the core potential and the earth potential. This arrangement improves voltage distribution in the dielectric of the cable, and consequently more uniform potential gradient is obtained. So intersheet grading side, the G1 max equal to V1 divided by T by 2. This is to be X into logarithm d1 by d, and G2 max similarly, this is to be as V2 by d1 by 2 logarithm d2 by d1, and G3 max equal to V3 by d2 by 2 and logarithm capital D by d2. So the G1 max equal to G2 max and G3 max equal to G max A. So the V1 by d by 2 logarithm d by d into V2 by d1 by 2 into logarithm d2 by d1 into V3 of d2 by d logarithm capital D by d2. So if we see the disadvantage of intersheet grading, firstly there are complications of fixing the sheet potentials as V1, V2, V3, and correspondingly the gradient side. Secondly, the intersheets are likely to be damaged during the transportation and the installation when this to be might resulted in the local concentration of a potential gradient. Thirdly, there are considerable losses in intersheets due to the charging currents. For these reasons, intersheet grading is rarely used. Thank you.